Ambush, I didn't fully review your notes. I didn't fully. Oh yeah, I haven't fully internalized the part about your version of two-level type theory, and
that's okay.
This Nikolai style definition of representability. So I started reviewing it a bit late, but yeah, I think probably we can fill the time, or maybe Ambush, you can talk if I get lost in in that part if we get there. Okay. So what are we going to talk about now? So previously we've seen an introduction to pre-shift models, and I think we stopped at introducing the definition of pi. So there was the definition of CWF, pi, sigma, but we haven't yet talked about universe or ID, or yeah, I think probably these two are the most interesting type formers, which we haven't yet covered. But today I will talk about some kind of generic stuff, some kind of generic theory related to pre-shift models. So I will talk about the yoneda embedding and how yoneda embedding can be used to do some reasoning. So for example, how we can use the yoneda lemma to derive definition of universe, and also functions in a way, of function types. But this is in scare code because some kind of functions can be directly derived from yoneda embedding, but I'm not exactly sure about the pi types, but we will also see that case as well. So this is some kind of generic theory related to pre-shift models, and probably we can also review a bit of category theory, because yoneda lemma and yoneda embedding is it's a very frequently used thing in category theory. And if you think back, so like the basic definition for a model of type theory is category plus extra stuff. So in particular, if you are talking about category theory, then category theory also applies to type theory. So applies to type theory to the extent that we are only using features which are also representable or which are also available in a particular model of type theory. So category theory works with categories, but it usually works with categories with lots of additional assumptions or lots of additional structure, and the same thing is true about type theory. So whenever we have some category theoretical result, then there is a chance that it also applies to the meta theory of type theory. Okay, so with pre-shift models, we assumed the category C, and the C category has the following components. So it has objects, it has some morphisms, and then it has composition, identity, and also all of the usual laws. So we assume that we have this kind of structure already, and then we define the model of TT such that every context is interpreted as a pre-shift over C. So Quan is interpreted as pre-shift over C, and you can think about the pre-shift over C as kind of a family of sets indexed over the category. or not over a category, but in this case, index concretely over this C category. So the way this is defined is that for any object of C, we get a set. So we have like a family of sets. And for every morphism of C, we get a function. I mean, here we have this kind of flipped arguments. So because the first argument is something which is in gamma I, and then the second argument is a morphism. But if we flip this argument, then we can see that for every morphism like this, we get a function which goes from gamma I to gamma j. So we have a family of functions. So every morphism is mapped to a restriction, so-called restriction function. And we also know that that composition of morphisms is mapped to composition of functions. So the C composition is mapped to function composition, and then C identity is mapped to the identity function. Okay, and if we want to define this P as like P-sheaf over C, so this P-sheaf is just some kind of naming convention. But if we want to be more uniform in our naming conventions, then or not more uniform, but we want to define like what is P-sheaf over C. Then we can also say that the P-sheaf over C is a functor from C op to set. So a functor is a morphism between categories, and in this case, C op is the is C, but morphisms are flipped, and set is the category of sets and functions. So functor from some C to D is a mapping between objects and a mapping between morphisms, such that it preserves identities and compositions. So it's a structure preserving mapping between categories, and in this case, P-sheaf over C is a structure preserving mapping from the opposite of C to set. And the opposite, so because we have a morphism from C op, that's why we have here this kind of flipping, because if I take a morphism from J to I, then I get a function from gamma I to gamma J. So C op means that this is some kind of a contravariant functor, so that if I have a C of Ji is mapped to a function from some gamma I to gamma J. Okay, so this is the basic setup, and if we say that whenever we have like every gamma context is a P-sheaf over C, then we can continue the definition of this model, and it is possible to extend it to the full CWF. So gamma is a P-sheaf, and the type. So if you have a type, then it's kind of a dependent P-sheaf, which means that it additionally depends on some element of gamma. And actually, we can make this a bit more precise. So let's make it a bit more precise. So there is this generic construction which is called the category of elements. So if we have any category, so if we assume that gamma, or we can also assume no. So what did I use? Oh, okay. So we just have a gamma, which is a context. So gamma is a presheaf. So gamma is a presheaf, and then I can take the category of elements of any presheaf. So it is an operation which turns any presheaf into a category. So, and this is called this integral. So it turns a presheaf over C into a category. Maybe I can do it like this. Okay. So the category of elements of gamma is defined in the following way. So the object in these elements of gamma is just a morphism. No, it's not a morphism. So it's an object of C together with an element of gamma over that object. So it's basically, you can think about this as a sigma, as taking a sigma of all components of a presheaf. So sigma of components of a presheaf. So the object becomes a sigma of a base object and something which is over that object, and the morphism. And the morphism becomes a morphism in the base category, such that we have this equation. Okay, I'm not sure. Maybe I can also skip over this, but the point here with defining this category of elements is that I can say that type over gamma can be defined to be a presheaf over the elements of gamma. And you can see it here because if you look at the definition of a type, we have like this implicit argument, which is an object of C, and then we get something which is over. And here's a type also. We have an object of C, and then we have an object of gamma, which is over that object, and then we get a set. And we can kind of just use a kerning to rearrange this. So we could also say that A is an I C gamma I arrow set. And if you look at this is an object in the category of elements. Okay. Okay, and what's a substitution? So substitution is a natural transformation from gamma to delta. So sigma, which is a substitution, it has an actual action on elements. So it maps every element of gamma to an element of delta. And here this is also kind of an implicitly quantified I, which is also natural. So it means that if we do a mapping, then a restriction is the same as first doing a restriction and then a mapping. So mapping commutes with restriction. And the TM is a dependent version, dependent natural transformation. So it's pretty much the same. The interesting change is that here this is a non-dependent function, and here this is a dependent function because elements of some type depends on some element of a gamma. Okay, and I think it makes sense to also talk in general about constant presheafs. So constant presheaf is, so let's call it this K presheaf. So it's an operation such that if we get a set, then we can turn any set into a presheaf. So if I get any set which lives in the meta theory, I can turn it into a con, but we previously defined con to be presheafs over C. Okay, so if I have a constant presheaf A, then So it's appreciative, but it's just constantly A. So the action on objects of the appreciative is just constantly the A cent. And the restriction does nothing. So this is indeed a constant appreciative because you can view it as a mapping which just constantly returns the A set, and that's it. Okay, but we additionally have something different, which is constant types or constant families. And I think Ambush probably mentioned this a couple of weeks ago. So previously we called this K, and then, but now because we have constant species, but we also have constant types, I think it makes sense to distinguish them and let's call one of them K species and the other one K type. Okay, so constant type takes a context, and then there is an implicit context, and returns a type. So constant appreciative, it returned appreciative. So it's appreciative which does not depend on the base category, but here this is a type which does not depend on the context. And we can create such a type whenever we already have a context. So we already have this context, then we can create a type in the appreciative model, which
So, but of course here the two contexts have to be over the same category, right? Because I noticed that you're not writing out the C arguments to con.
No, we are. So we already assumed the C on the top level, and now con, tie, whatever, every component is in this appreciative model. So whenever I'm writing con, it means appreciative over C, and whenever I'm writing tie, it's a dependent appreciative over C, and so on.
Right, so the base category is set in stone. Well, except for the constant appreciative, because that.
I mean, for the constant appreciative, from any set, I can return a con, but the con is defined to be appreciative C.
Okay. So by the way, I have a question about that. So so you start with a category, and then we build up the pre-sheaves as context, and then we build from those the types and then the terms. But once we have this big edifice, what is the intuitive role of the base category in the resulting type theory? Like how do the properties or the choice of base category, how does that translate to what exactly we get at the top of this building?
I don't really have an intuition for that, because we can get like an enormous range of models depending on the base category, and they can be very different. So for example, if we choose C to be the singleton category, then we get the set model, and we all know about the set model. But if we choose C to be the category consisting of one arrow, then we get the family model, which is kind of a parametric model. If we choose C to be like some kind of cube category, then we can use this to build a model of cubical type theory, and so on. So it can be very different depending on what C we choose.
My intuition is that if you choose a C, then you basically embed everything in C into your type theory. So András will show the yoneda embedding, and that's what it does. So if you add some stuff in C, you add some substitutions in C, then so first, if you add some objects in C, they will become contexts in your new model. If there are some morphisms in C, they will become substitutions in your new model. So if you add more stuff in your category, they will end up in your theory. So I mean, so basically, if you think about contexts as types, then each object in your category gives you a new type. and each morphism in your category gives you a new term between the corresponding types, which goes from one type to the other.
Mm-hmm. And for example, in the family model, how does this exactly work? So if I have a like this,
well, in the family model, there are just two objects and one morphism. So you will get two types for this. So one type is the like the base thing, and the other is the thing which is over it. And then with the morphism gives you the map, the projection. Right. So you have a yoneda of 0, which will be a presheaf, and you have yoneda of 1, which will be another presheaf. Yeah. And then you have a, yeah, exactly, from yoneda 1 to 0, right? Yeah, in the other direction.
No, right?
Oh, yes, you're right. Sorry. Yeah, you're right. Mm-hmm.
Okay, but I still don't quite see how this. So how I can view this in the family model. So we have two contexts, and then we have a morphism between the two contexts. But how does that work if I want to?
So, I mean, yoneda of 0, they are substitutions into.
All right.
Right. Maybe it's better to think about that. Yeah.
But I mean, not really. I mean. I mean, yoneda of 0 would be like a presheaf, but it's just a unit like this, just a singleton set, because only identity goes into 0.
Mm-hmm.
And yoneda 1, it would be like there is just one, okay, two arrows which are going into one goes from 0 and the other from 1. So I still don't quite understand how this can be used. Okay,
let me think about it a bit.
Okay, let's continue.
Yeah.
So I mentioned that there is a way of making a presheaf which does not. So this does not depend on C, but I can make it a bit more like it constant as a type. So this is a type which does not depend on the context. So there are like two dimensions of being constant, because there is the type dependency dimension and there is also the base category dimension.
Sorry, you have two cons in the definition of k-type.
Yes, that's intended.
But okay, but then please explain. Also, below, 2 lines below, it only has just, okay, the second one is implicit, but okay. So
okay, so let's make it a bit more explicit. So if I have a k-type of delta, so, and also I have an implicit argument gamma, then this becomes a type in gamma. So yeah, so now this vertical bar, this defines the action of this particular type on objects of C. So then if I get an object of C, but I also have to mention an element of gamma, which is over I. So this is a base object, and this gamma is has type has type like gamma I, and then I have to give a set. And then I just define this set to be an element of delta. And I should also define.
To clarify, so are you saying that for any gamma context, this set of types will be just the types over the fixed delta context?
Say again, please.
So it doesn't depend on gamma, but it's always written somehow that. Okay, I don't see what it's written.
Yeah. So it does not depend on gamma. So that's the point. That if a type is constantly delta, then it just calls the action of delta, and it doesn't care about this gamma or this gamma. But we still introduce this gamma as an argument because I want the result to be a type in any gamma. So
okay, and why is it somehow? So on the right-hand side, you have something which is a context, but you interpret it as a type, and it's just a bit strange at first.
I mean, yeah, I mean, it's strange, but this is actually, I mean, a pretty simple thing which is supported in a lots of models. So K-type just says that if you take any context, then you can view it as a closed type which does not depend on anything, right?
Yeah. Okay.
So you can view any type in context as just some kind of product type which does not depend on anything, and that's why you can create a type from any context which lives in any other context.
Okay.
And then there is if you define K-type like this, then we also have this isomorphism, such that a term which goes from gamma to constant delta is just the same as a substitution from gamma to delta. And sometimes this is called lam k or lat k. And this is kind of like the term format for this K-type is given by this lam k up k isomorphism. So if you have a Tm gamma, then kt delta, then you can view it you can view this as some kind of record type, which does not depend on the context. So like it's a non-dependent record type, but it's the same thing as having a substitution from gamma to delta. So if in gamma you can give every component of this record, it's the same as having a substitution from gamma to delta.
So this is basically turning, but this goes the other way as well, right? So this means you can turn any substitution into a record of sufficient arity.
Right. Yeah, you can take any substitution and then turn it into some record term. Okay, and now we have, for example, that so the empty context in the preshift model can be defined to be the constant preshift, which is just constantly the unique type. And this is actually, it's the terminal preshift. And it's also the empty context in the preshift model. And then we have like a bunch of stuff, which I think, so these were covered previously. So we also have the ID, which is the sub gamma gamma, which is the identity natural transformation. And we also have composition and so on. And then we also have type substitution. So for type substitution, if we have a type in delta and then we have a substitution from gamma to delta, then we get a type in gamma. But this is quite simple, so it's kind of defined as a composition. So A has some action on objects, and on elements, and also so A turns an element of delta into a set, and this is a natural transformation from gamma delta, so we are just doing a composition. So A substituted with sigma, the action of this on gamma is the action of A on the action of sigma on gamma. Okay, and then we also have this context extension, and context extension is also defined pointwise. So you can view it as a sigma of presheaves. As a sigma of presheaves. Yeah, so the first component lives in gamma, and then the second component lives in A, but it also depends on the first component. And then using this definition, we can also define PQ and the substitution extension operations with all of the equations. So this is kind of the definition of CWF. And I think now we should continue with the yoneda embedding and also yoneda lemma. So this is a kind of a generic category theoretical result, but we can also use here when we are doing type theory. Okay, so just to give some intuition, there is something like in any category. So in any C category, now let's forget about the assumed C category for a bit. So let's just assume that this is any category. So we have this, which is the family of sets of morphisms. So this goes from C to C to set, right? And we can also think about it as this kind of like two-argument function which goes into set, or we can think about it as this. So in any C category, we already have this kind of like set family available. So a very kind of a basic way to create a functor which goes into set, if you already have this C category, is to just use this, right? And this is called a home functor. And the home functor is just using this component, which is already available in any category, to create a functor which goes into set. So we say that it goes from C of C to set. And how is it defined? So maybe let's call it. Let's call it home. Okay, so this naming is not very important. It's just some kind of historic naming in category theory. So home is a functor. So home is a functor. And a home ij is just defined to be C of ij. So whenever I have an object of C op and an object of C, I just return the set of morphisms. And then whenever I have some F and some G, so this action on morphisms, but we don't really have any notation for that. Okay, so let's just, so if we have an F, which is a C, which goes from A to I prime, and then we have this which goes from J prime to J. Then we want to map it to a function. And probably I'm going to be a bit confused about this. So if we have and I J prime to C I prime J. Is that correct? Okay, but maybe I should probably mention like this product of categories, right? So we haven't yet talked about what this is. Is that correct?
Yes, I think we haven't discussed it.
Okay,
we haven't discussed the category model, and this would be something in the category model.
Okay, so first let's just talk very briefly about this product. So it's not very complicated. So it's a product of categories. So if we have, so assume that we have CD, which is a cut, then we have C product D, which is also a category. And the way it is defined is that an object in CD is just a pair of objects. So it's a pair of C and D. And the morphism. So in this category, the morphism from an ij to an I prime j prime is just a morphism from I to I prime, and the morphism from j to j prime. And then we can also define the composition component-wise. So if I have an fg, and then or maybe if I have an f prime and I have a g prime, then this is just defined to be fg and f prime g prime. Yeah, and then probably I should also write this as I prime and then j prime. So then we have something which goes from I to j, and then we have something which goes from I prime to j prime. So what happens here is that we are just taking the direct product of two categories, so we are duplicating everything. So we have pairs of objects, pairs of morphisms, and then operations defined component-wise. So this is a product of categories, and then I say that for every C category there is a functor called home, which goes from C of C to set. And the way it is defined is that if I have some I prime, probably this is the better notation. So the I prime comes from C, and the I comes from the CO. And then this is just a set of morphisms. And if I have a morphism, then I have to map that into a function. So this is mapped. Let's just keep the indexing the same way as before here. And I can define this to be, so if I have like a mapping of f to, and now I have to do some pre and post composition. So okay, so here I have two morphisms, f and g, and I also get some h. And the way it works is now I have to do a pre and post composition, but I f h g, or is it the other way around? So I go from I to j prime, so something which
maybe just draw a commutative diagram and then it will be clear.
So it's I to j prime. So is there something which goes into I? Not really. Okay. So there is something I to I prime. No, this should be the other way around. So I to J.
Just draw a square, and then it should be clear of the picture.
Well, only one of the two possibilities is type correct. So if you try to
yeah. Okay, so I have an F and I have a G, and then okay, so how does this works? And then I want from an I prime J prime, so I prime J, I want to go to I J prime, and so I have to go from I to J prime, and H. Okay, I don't really understand, but I think you get the idea. So this is homework. Okay. But in any case, it's going to be pre and post composition. So this is going to be. Yes, and I'm pretty sure that it's this kind of pre and post composition. So F, H, and G, because this G should be covariant and the other one should be contra. Oh no, then it's the other way around. Okay, I should have reviewed it, but I think this should be kind of clear. So this is the home functor. And then how do we get the yoneda embeddings? So yoneda embeddings. So we already have a functor which looks like this, and now we can say that we already have the home, but it is possible to do currying in functors. So if we do a currying of home, then it's going to look like this. And then we can also, so this is by currying we get this, and by flipping the arguments we can also get this. And this is actually so the flipped version is called, it's the contravariant yoneda embedding, and the non-flipped version is called the covariant. Okay, so and the one which is going to be relevant for us is the contravariant version. So I mean, in this in Meta's theory of type theory, we are usually the contravariant version is relevant to us. But the covariant version is also interesting because it has some kind of more intuitive functional programming examples are a lot more common if we are using the covariant yoneda embedding. And I will give some examples using this one as well. Okay, so now we just call yoneda embedding y. So this is the contravariant version, and if we take any object of C, then so this is the action on objects. So action of yoneda embedding on objects, but we just call it y. And it turns any object of the base category into a con which is a presheaf over the base category. Okay, so this yoneda y. So if we assume that y and not y, I. So if we assume that I is an object of the base category, and the yoneda I is a presheaf, So it returns a set for every object, and then what happens here is that yoneda I of J is the set of morphisms from J to I. So a yoneda I is kind of C morphisms into I. And this definition also falls out of this definition if you take the home functor and then you flip it and then you do a currying. Okay, so Y gives me a con for every object of C, and it also gives me a substitution for every morphism of C. So if I have some F, which is a morphism from I to J, and then it gives me a substitution from yoneda I to yoneda J. So it gives me a natural transformation from yoneda I to yoneda J. And if you look at it, because the elements of yoneda I are morphisms into I, so here I have an element of yoneda I, which is this G, which is a morphism into I, and I have to return a morphism into J. So convert morphism into I to morphism into J. And we can do that because we already have this F, so we can just compose F with G. And now, if we want to show that this Y operation is actually it's a functor, so we want to show that Y is a functor from C to presheaf C. So it's a functor from C to con. And we also have to show that it preserves the identities and in the compositions. So we also have to show that the yoneda F applied to ID is ID, and the yoneda F applied to composition is also a composition, but this ID is the ID from the presheaf model. So ID from presheaf model. And this composition is also from the presheaf model. This is the identity natural transformation, and this is a composition of natural transformations. And this is quite easy. So this is a possible homework to do. And I left out an additional detail here. So this is a sub, right? So we also have to show that this is a natural transformation, so plus naturality. So every substitution has two components. If you go back a bit, yeah. So every substitution has an action on elements, and then it has this naturality condition. Okay, so we have defined this embedding, and now an interesting observation about this yoneda embedding is that it's bijection on morphisms, and in category theory, it's a functor which is a bijection on morphism is called fully faithful. And full means usually surjection on morphisms. So a functor is full if it's a surjection on morphisms, and it's faithful if it's an injection on morphisms, and it's fully faithful if it's a bijection on morphisms. You can also ask, like, why do we need all these kind of stupid names? I am not completely sure, but it makes a bit of sense because when we are talking about functors, so we cannot just say that a functor is injective or bijective or surjective, because a functor has two kind of actions. So it has an action on objects, and it also has an action on morphisms. And this full and faithful, it only refers to morphisms, which is important because sometimes we also want to talk about some surjection or injection-like properties on objects, but then we do not say that it's surjective or injective on object, but usually instead we use some kind of essentially surjective. So what about objects? Action on objects. So for action on objects, we say that it's kind of just surjective or injective up to isomorphism of objects, which is called essentially surjective or injective. And the reason is that in category theory, it's not a very nice thing to talk about equality of objects, because we want isomorphic objects to be. We do not want to distinguish isomorphic objects. So that's why we say that surjectivity or injectivity on objects should be only defined up to isomorphism of objects. So this means that if I have a functor which goes from C to D, then I want to talk about surjectivity, like if there is, so an f of I is an object, so if I is an object of C, then I have an f of I, which is an object of D, and essentially surjective for this would mean that for every j which is in D, there exists an I in C such that f of I is isomorphic to J, but not equal to J. So probably we should also kind of refresh this tilde. So whenever we are using this tilde, this means isomorphism. So in a category, an isomorphism, but probably we have seen this in some ways, but let's just make it a bit more exact. So Ij, if there is some f which goes from I to j, and g which goes from j to I, such that fg equals identity, and also gf equals identity. And this kind of isomorphism, so whenever we are using tilde, there is some implicit category involved. So for example, if I want an isomorphism of sets, so if I have some isomorphism of sets A and B, then this is kind of a pair of functions such that the functions compose two identity functions. But I can also talk about an isomorphism of contexts in any model of type theory. So I can talk about this. So this is really a pair of functions, but because a model of type theory includes the category of context, an isomorphism of context becomes a pair of substitutions. and a pair of substitutions such that they also compose to identity substitutions. But both are just special, so these are the special cases of isomorphism in some arbitrary category. Okay, and yeah, and then so what's this interesting property of yoneda embedding? And the property is that so this yoneda embedding is a bijectional morphism. So this means that if I have the set of morphisms from I to j that's isomorphic, so this is an isomorphic as a set to to natural transformations or substitutions in the preshift model from yoneda y to yoneda j. And this can be quite useful because it means, like, for example, if I want to show that that in C, so if I want to prove something about morphisms in the base category, like I want to prove that there is an isomorphism between I and J, then it is enough to show that there is an isomorphism in the preshift model. Okay, because the two sets are in bijection. Whenever I have an isomorphism here, then I can convert it to an isomorphism here. And likewise, whenever I prove that there is no isomorphism here, then that also proves that there is no isomorphism here. So this can be used as some kind of extended way of reasoning about the base category. And also, so whenever I have an F from CD, which is fully faithful, I call F, or I can call F to be an embedding, and that's why Y is called is yoneda embedding. We can also, so whenever we have a functor which is fully faithful, we can also use it as an embedding of a subcategory. So this means that for every C object, we get a D object, and this marks a subcategory of D. So inside D, we have like the image. So we have all of the objects which come from a mapping by F. And not every object in D comes from C. So this is not the entire D category comes from C, but whenever we have something which is an embedding of a C object, then we get all of the morphism between those objects. Right? So it's kind of a subcategory. So C can be viewed as
a full subcategory because it's full, not only faithful, right?
Yeah, I think it's a full subcategory if whenever I have a full functor, right?
I think so. So it's not only the point that it embeds everything, but anything between yoneda of C and yoneda, or anything between F of I and F of J comes from C. So it's right. So there are other things in D than things coming from C, but if you look at the morphisms between two things from C, so come from C. So
yeah, so F is kind of, if a subcategory, so you can view it as a subcategory of D with like some objects of D, but all morphisms of D. So we can draw like a bunch of objects and then a bunch of arrows, and we can say that F denotes a subcategory which contains some objects, but whenever I have two objects which are in the subcategory, then I get all of the more original morphisms of in the subcategory. Okay, and how can we prove this? So the way that we can prove this is by first proving the yoneda lemma. The yoneda lemma.
Great. I figured out the question. So with yoneda lemma, we can see how the families model. You can refer to the two different sets. It's just yoneda of 0 ROA and yoneda of 1 ROA.
So yoneda of
0 ROA internally, it's the same as the 0 component of A by yoneda lemma. Yeah, exactly. Yeah.
So this is the same as A0.
Yes. Yeah. So that's how you can internally talk about the two, get a language of talking about the set, and you also get the morphism, right?
So no, there is just a yoneda F would be a sum between yoneda 0 and yoneda 1, which is a natural transform.
I think this is a nice application, yeah. Or maybe the simplest example of using something internally.
Okay. Yeah. So how do we show that this holds? So I want to show that there is this isomorphism. So this is an isomorphism of sets, but actually this is also a natural isomorphism in I and J, but probably that's not too important for us now. Okay. So I want to show this yoneda lemma. So I have to define two functions. So let's call it maybe to and from. So if I have a substitution from yoneda I to gamma, then I want to get an element of gamma. Okay. And the way I can do it is just to, so here I have a sigma, and so this sigma has an action on elements of yoneda Y, but yoneda Y elements are just morphisms which go into Y. So this I dy is actually an element. So this is a C which goes from I to I, but it is also an element of yoneda Y at Y. So if I pick this morphism, then I can use the action of sigma to map it to an element of gamma. And how can I go in the other direction? So if I have an element of gamma, then this should be a natural transformation from yoneda I to gamma. So I already assume that I have this gamma here, and then I have to map an element of this to an element of gamma. And an element of yoneda I is just a morphism which goes into I. So there is some morphism which goes from J into I, and I have to map it to an element of gamma at J. But I already have this one, and because I already have this, I can just use a restriction of gamma, which is over J. So I can do this definition. And then I also have to prove that So here I would also have to prove naturality. So whenever I am returning a substitution, so here because this returns a substitution, I also have to prove that this is natural. I'm just copy pasting here the naturality. But we can also look a bit at this. So if I am using from gamma, so if I'm applying from gamma to a restricted thing, then that's the same thing as first doing the application and then the restriction. And this just follows from all the definitions. So in particular, if this restriction here, so this restriction happens in yoneda, but restriction in yoneda is just composition of morphisms. And if I do this and then I use yeah, so first I just unfold this restriction, and then I just unfold the definition of from, and that's why it works. And then I also have to prove that these are inverses of each other. So one side is that I have to prove that a from of 2, so from composed with 2 is identity. But here on both sides I have a substitution. So I have this on both sides. And whenever I want to prove that 2 substitutions are equal, it is enough to prove that the first components are equal. So I only have to prove that the actions are equal, because the naturality is basically some kind of proof irrelevant thing. So if I have uniqueness of identity proof in the meta theory, which I think we have, then I only have to care about the proof relevant part of every substitution. And the same thing is true of terms. So I only have to prove that the actions of terms are the same. Okay, so if I have this, then I'm just applying it to some. So I'm applying both sides to some f, and I'm taking the action component of the both sides, and this is what I have to prove, and it can be proved. And then the same thing in the other direction. This can be also homework to check this derivation, or even to redo this. Okay, and now we have the yoneda lemma. So we already have this yoneda lemma. And now we can just instantiate the yoneda lemma. Show. So the yoneda lemma is this isomorphism. We have this, and then we want to show this. And in this case, we can just choose gamma to be yoneda j, and then from the yoneda lemma we get that sub yoneda I yoneda j is isomorphic to yoneda j I. But by definition of this yoneda embedding, this is the same thing as a C from I to j. Okay. Okay, so this is the yoneda embedding. And but maybe I should also give some Haskell examples. So in Haskell, the contravariant yoneda lemma would look like this. So this would be the contravariant yoneda. So whenever I have some contravariant functor f in Haskell, but But in Haskell, we care about, or I mean, in practical programming, we are using the functors which go from type to type. So the C is category of Haskell types and functions. And then this contravariant F is a contravariant functor which goes from husk to husk. So C is sometimes called husk. And this husk category behaves a bit like set. I mean, it's not literally the same as the category of sets because I mean, it's not the same. So we have like different properties of this husk category than the category of sets, but usually we are hand waving in Haskell programming that we say that it's the same thing as a category of sets, and we say that the Haskell types correspond to sets. Okay, so the contravariant yoneda lemma says that if I have a function like this, so if I have this polymorphic function for j, if there is a function from j to I, and then it goes to fj, then this is isomorphic to f of I. And the reason that this is a sensible definition in Haskell, because we have parametricity in Haskell, so this is automatically a natural transformation. So on the left-hand side, we already have a natural transformation, and as we've seen, so the yoneda lemma says that the natural transformation from yoneda I to gamma is isomorphic to this, but in Haskell, you can just convert it and like that. So this is automatically natural, so this is already correct. But this is not very commonly used in Haskell. So in Haskell, we usually instead use the covariant version of the yoneda lemma. So if I have a functor f, then I have a natural transformation which goes from reader I to f, then it's the same as f of I. And then there is a very simple example. But for example, let's assume that f is just the identity functor. Then the yoneda lemma says that this is an isomorphism. And this isomorphism just says that we have a church encoding of the identity functor. And usually so yoneda, so the covariant yoneda is called reader in Haskell. So you type reader A, B is, or so this reader is actually just the home functor, but we can already do a partial application, so it's already in a curried form in Haskell. So the covariant yoneda can be just defined to be a reader. Okay, so this is about yoneda, and then maybe there is another kind of an interesting observation about yoneda embedding. So let's first just define the natural numbers, and now I say that the type of natural numbers can be defined as so first we take the constant presheaf, which is just a presheaf. So the constant presheaf is just a con, and then we can take the constant type of this. So this is something which is kind of doubly constant. Okay, and so this is the definition of natural numbers, but in general, we can take, if we have any set, then we can also just take the constant type of the constant presheaf, which will be a type in any context. So this means that any meta-theoretical, so any meta-theoretical set can become a type in the presheaf model, and of such types we can also show the following isomorphism. So if we have a term which goes from some yoneda to this k-type k presheaf A, then so this is by the definition of k. K-type, so this is kind of the defining isomorphism of K, and this is a yoneda. So it's the same as a morphism from yoneda I to a constant presheaf A, which is by the yoneda lemma the same as the element of constant presheaf A at I, which is the same by definition. So this is by the definition of constant presheaf the same as A. So you have this kind of thing, and yeah, so what does it mean? It kind of means that if we are including an external set to the model, that cannot really depend on things like on morphisms of the base category. So every such term actually must be just something which constantly maps to A.
But if you add the type like this, what can you do with it internally?
I think this question is related to two-level type theory. I don't think I have a good answer. So you can kind of view it as a preliminary to two-level type theory that we show that we can include any meta set into this model. Yeah, but I don't know any good example at this point.
No, well, maybe that's not what I mean. What I mean is that I don't mean what is this technique good for. I mean, what is it that you can then do internally with this net? Like, I assume you can't eliminate it using natural induction because you don't really know anything.
We can. So net supports 0 sub nothing beta. It supports everything. So if we take this to be the definition of net tie in the presheaf model, then it supports all of the usual components of natural numbers.
But wait. But you don't mean by somehow add you don't mean adding these as well by fiat. You mean just by having this type, you somehow have access to the details of the type from inside from the object language. Is that what you're saying?
I don't really understand the question. So the thing is that if I have like a syntax of type theory, and then I have a natural number like usual, then I can just use the meta-theoretic natural numbers to interpret these natural numbers. But and in two-level type theory, this natural number would be the meta natural number, but it will be also possible to have a different natural number type, which is the object theoretic natural number type, and it also has an interpretation, and the two are not the same.
I don't feel like this answers my question.
So this is just a technique to move anything which you have in your meta theory into any presheaf model. And you can see that what you included from the meta theory, it doesn't interact with the stuff which comes from the category. So this is kind of the opposite direction of yoneda. So yoneda gives you stuff which was in the category and puts it into the presheaf model. And using constant presheaves and constant types, you can include anything from your meta theory into your.
But that's what I'm asking. Like, are you really including like? Can you then write a program in your object language? Well, I guess program might not be the right term, but can you write some type theory term in your object language, which which uses this net, uses the netness of this net and not just as a black box type? Like, okay, let me put it this way.
Exactly.
I can see,
for example, the netness means that it has a recursion principle. And
yes,
that recursion principle works the same in the presheaf model. Yeah.
But how do you even write that down in the object language? Like, how do you even refer to the to recursion on this type?
So in the object language, you don't refer, you don't get immediately access, but you can, if you look outside in the definition of the presheaf model, you can just define it as the constant induction, right? So you have some induction principle externally, and you just use that external induction principle to define the internal induction principle using this constant stuff.
Right. So I guess that's what I meant. That if you add not just net, but you also add zero and suck by having some meta.
I mean, you can already see that. Okay, if you go forward a bit, then it will be immediate that in some situations, like this can be defined, like all of the usual components of natural numbers can be defined. Okay, I think let's go there a bit.
No, but I mean, I can see how you can do that if you define each of these things in the external level. But what I'm saying is, just because you add the type, just because you say, okay, now you have this extra type by fiat, go and have fun with it in your object language. That doesn't mean you can do anything with it in your object language, right? If you give me the full kit, if you tell me that, okay, I have this extra type and I also give you these extra terms, then with the whole package, sure, you can do things. But if you only give me the type, how does that give me anything other than a token I can pass around and never look inside?
So the point is that so we can define the type, but also we can define not as a type, but we can also define everything which comes in the kit. So we have the usual natural numbers. So we don't only have the type, which is this not, but we also have everything else.
Yeah, but that's only if you give all of these separately, right? It's like from the inside, I can't reach out and define zero if all I have is all these syntactic terms plus this type called net. Then I can't reach out to the meta level to get a hold of zero, right? I guess that's my question.
Yes, because I mean, so the way this works is that, so if I want to interpret some syntax, then I have to specify every component of the syntax. And if I only specify that there is a not, which is a type in gamma, then I can interpret that with like lots of things which are actually not even natural numbers. So if I want to have natural numbers in some syntax, then I have to say that there is a suck and a zero and induction principle and so on. But this is kind of an informal way of saying that that if I have this in the presheaf model, then it also supports all of the usual components of natural numbers. So I mean, in the syntax, it would not be derivable from anything. If I skip, for example, if I skip 0 in the syntax, then I don't get 0 from anywhere.
Right. Yes, okay, that's what I meant. Yes, and then so the claim is just that, but you can expose 0 from, but at the meta level, you can give definitions of a term which you can then use in the syntax to stand for 0, and you can do that generically over the category. Okay, I think
I mean, it means that any pre-shift model supports natural numbers. So that whenever, so any pre-shift model has natural numbers, so that so a pre-shift model is just a particular model of the syntax.
If the meta language does.
Yeah,
of course, sure, yes.
Yeah, but I think you can also make this a bit more precise but then you need a generalization of the pre-sheaf model, so not pre-sheaves into set, but pre-sheaves into an arbitrary category, and then you can make statements like, if a model of type theory supports natural numbers, then pre-sheaves over that model or pre-sheaves into that model also support natural numbers. But I don't know about any formal proof at this level of generality for type theory, but I'm sure the category theorists have all worked this out already.
I mean, but the induction is already, paper is already very similar to this, no?
Yes. Yeah.
We have like if some model supports this, then it also supports this.
Yeah, exactly. Yeah. And this is what we are trying to do with SUMI. So if a model of type theory supports inductive types, then you can obtain another model which supports QIITs. For example, that would be an analogous result. Yeah.
Okay, so that's a bit about, yeah, so it's kind of a bit about terminology, is that there is a representable con. So if I have some gamma con, then it is representable if there is some I such that gamma is isomorphic to yoneda phi. So every context is representable if it's of the form yoneda of something. And then we can ask the question. So for example, is the empty context representable? So this con, and so the definition of this is just the constant pre-sheaf top so is the terminal pre-sheaf representable, and it is representable if we assume that there is a terminal object in the base category. So we need terminal object in C, and we can call it like empty context, but in C. So let's use this subscript. So this is an object of C, and then we also know that it is terminal. So there is this epsilon C, which is a morphism from any I into this, and we also know that this is unique morphism. Okay, so if we have this, then we can also show that the yoneda of this is isomorphic to this in the pre-sheaf model. Okay, so because the yoneda of this is, if you look at what happens, so this is just defined to be the set of morphisms into this. But this, as a set, it's isomorphic to just simply to top. And this is defined to be just top. So we can easily show that that the yoneda of terminal object is isomorphic to the terminal object in the pre-shift model. So this means that yoneda preserves terminal objects up to isomorphism. And a stricter version of this preservation would be, so this is kind of yoneda weakly preserves terminal objects. So it's a weak preservation. And the strict version of this preservation would be just to say that yoneda of terminal is strictly equal to terminal. And this would be the kind of strict and also the evil version, because it talks about equality of objects. And we want to avoid talking about equality of objects usually in category theory. Okay, so now we have this preservation, and then we can also say a bit about terms in the empty context. So if I have a term in the empty context, which is again of this meta-theoretic type, then this is the same as the sub. So by the preservation of the empty context, so this is actually isomorphic to yoneda of this. And now, because this TM now has this yoneda form, I can just immediately see that this is isomorphic to A. So for example, a TM, so an empty natural number is isomorphic to the meta-theoretic set of natural numbers. Okay, so this is the empty context. Because yoneda preserved the empty context, now we know that the empty context is representable. So we can use this yoneda reasoning about the empty context. And if we also know, so if C is actually a CWF, then additionally we have types in C, and we have terms in C, and we have context extension in C, and then we have PC, QC, so on. So we have all of the usual CWF components in C as well. And in this case, we can also show that a yoneda of I, C, but now we are kind of running out of notation, because usually, so if C is a CWF, then it has like this type theoretic structure, but previous notation only had like I, J, K, and so on. So now an I is a context in C, but I can use the context extension in C to extend it with some, I'm not sure, like an alpha, which is a type in the base category. And then I have this isomorphism that yoneda also preserves context extension up to isomorphism. So it's a yoneda I. And yoneda alpha, but then I would also need to define the yoneda embedding of types. Base types. But we can also show this. So it means that the yoneda embedding preserves context. And now we have a lot more representable things in the pre-shift model, because this preservation says that the empty context is representable. And from this, we get that an extended context, sorry, this is not C. So an extended context is also representable if the type is representable, and if also the prefix of the context is representable. So by these two lemmas, we can show that lots of contexts are representable in the pre-shift model. Okay, and it's kind of important because this yoneda reasoning, it only works if I have a substitution or a term from something which is representable. So the yoneda lemma. I need to have some sub. Okay, and okay, so what else do we have? So we have universes, and we also have exponential objects, and maybe we can talk about the universes first. Okay, so this is a universe, and this is one kind of universe, but it's kind of the standard notion of universe in the pre-shift model. So what we want is a U con such that a substitution from gamma U is isomorphic to types in gamma, and this is called a cocon universe. Okay, so let's do some recap. So previously we said that the cocon universe consists of some EL and C, which is an isomorphism between Tm gamma U and Ti gamma. But actually, if we have K Ti, then it's enough to define this isomorphism using substitutions, and let's say that U is just a context, U as con, and then we have an ELC, which is an isomorphism like this. So it's a sub gamma U is the same as a Ti gamma, and then we can recover the usual universe as just a constant type. So this is not very complicated. The point here is because in this model we have constant types, we can use it to make our job simpler, because it's a bit simpler to work with substitutions and context than to work with terms and types, right? Okay, so how can we define this? So now I have to define a U which is a con, and the UI should be some set. Okay, so the UI should be, what kind of set should it be? And now we can actually use the yoneda lemma to derive the definition here. So we can use it first, because I know that I by the yoneda lemma has to be isomorphic as a set to sub yoneda y U. But so this is, I already know this, that whatever the definition of UI is, then by yoneda there is an isomorphism here. But I also know that because I want to have a cocon universe, or I want to have some kind of cocon universe, or even a slightly weaker Tarski universe, by requirement of cocon universe, I want this isomorphism to also exist. Like. So if I look at this picture, I can just say that, well, then let's make the definition of UI be just Ti of yoneda I. So I just say that this is Ti of yoneda I. And because I have this definition, now actually this is a strict equality. So now UI is just defined to be strictly equal to tie of yoneda I, but definitely that has to work, because in that case I already know that this has to be an isomorphism, but now I have a strict equality as well, so I know that this should hold as well. Okay, and now I can define actually all of the components of this thing. So, for example, if I want to do a restriction of an element of the universe, so if I want to do a restriction on U, then I can use type substitution to do it. So here I have an A, which is a tie in some yoneda I, but actually, so it's an element of UI. And then I also have a morphism which goes from J to I. And then I want to return an element of U at J. And if I compute all of the types involved along the definitions, then it means that I have, from a tie over yoneda I have to return a type over yoneda J. And then I can use the embedding of this F as a substitution, and I can use the type substitution in the pre-shift method. And similarly, I can also define EL and C as well. Maybe it could be also homework. To do all of this, and this is called. So this is called the Hoffman Streicher universe. Okay, and what about functions and exponentials? So this exponential is kind of an easy case. So the kind of a simpler version of function types. So exponential object is a simpler version of function type. So in any category, if I have two objects, then I can talk about the exponential object, and it behaves like a function object from one object to the other object. And why are we looking at exponential objects in the pre-shift model? So the reason that we are looking at it is because it's also, so it's a very simple application. So we get it as a simple application of yoneda, and then we can use it as an inspiration. We can use the definition as kind of a template for the pi-type definition. And the pi-type definition is a bit more complicated, and probably it can be also derived from some application of yoneda, but I'm currently not very familiar with it. So it's a good strategy to first use the yoneda lemma to define exponential objects, and then use the dependent version of exponential objects to define pi types. Okay, so what are exponentials? So it's kind of a weird function type, because it's a function type which actually it does not refer to terms or type. So like a function con and doesn't refer to tie or tm. But we can see that it still makes sense, and in general there are categorical versions of type theoretic constructions, type formers. For example, the exponential is a categorical version of like simple function types. And we can also have a categorical product which is the categorical version of a product type. And likewise, we can have a categorical coproduct. Which is like this coproduct or some type. Yeah, so for this kind of simply typed typeformer, there is usually also a categorical version, and the main difference is that the categorical version, the categorical versions don't refer to types or terms; they only refer to context and substitutions. And in some cases, it is possible to derive one from the other, but in general, it is not possible to derive categorical versions from type theoretic versions or the other way around. Okay, so the exponential is that we have some, let's call it arrow, so it is a con, and we can also have a lambda and an application. So there is a defining isomorphism, which is that a substitution from a gamma delta to, let's call it maybe, let's call it sigma. So this should be isomorphic to a substitution from gamma to delta sigma. And if we think back to the type theoretic version, so the type theoretic version of simple function types would be that the Tm of gamma A B is isomorphic to Tm gamma of A. So this is the categorical version, and the other one is the type theoretic version. And for this, we also need the categorical product type, right? So, but the categorical product type is probably what we would expect. So we can take the product of two contexts. And you can, I mean, syntactically, you can view the product of two contexts as just the concatenation of two contexts, such that there is no type dependency. So the second context is also just a well-formed standalone context. So we have this, and then we have a first projection, which is a substitution from gamma delta to gamma, and then you have a second projection, which goes from gamma delta to delta, and then we also have a pairing. So if I have a substitution which goes from delta, and if I also have a substitution which goes to sigma, then I have a substitution which goes to delta sigma. And here you can also remember the usual type pairing for type theoretic products, and which would be Tm gamma A and Tm gamma B and Tm gamma A. So this is the product, and we also have some beta and eta rules as usual, and this is the exponential. So here we have this defining isomorphism, and in particular we could say that there is a lambda which converts this substitution into a function, and then there is also an application. Okay, and now we want to define this exponential in the pre-sheaf model. Okay, so we want to define exponential in the pre-sheaf model, and but now what we have is that, so we want to define this concretely con, and I have to define the action. So I have to define the action on objects of the base category, right? And this should be some kind of set. But what should this be? And now we can again use the yoneda lambda, because we have that delta sigma I is isomorphic by yoneda to a substitution from yoneda I to delta. This is isomorphic by the requirement of the exponential object. So by the defining isomorphism of the exponential object, this should be isomorphic to some yoneda delta sigma. Okay, and now because we have this, we can just say that this should be the definition. And then it works out, so we have like all additional components, and I won't write out like all of the additional components, including the application and lambda and whatever, and also like the restriction. So here I also have a definition of restriction. I'm just copy pasting it here. So you have plus all of the additional components. But one interesting thing to note here is that this looks very much like the Kripke function space, because a natural transformation from yoneda y times delta to sigma. So if we are unfolding the definitions, so some yoneda y delta sigma at some j. So it has some so just the type, what I want to unfold. So this is such that for every j, so for every j, if I have a morphism from j to I, because that's the definition of yoneda I get a morphism from j to I. And then I have an element of delta at j, and then I want to return an element of sigma at j. And if you're the kind of person who's familiar with the kind of normalization by evaluation with the MBE, like the normalization by evaluation of some simple type theory with the Kripke semantics. So compare MBE with Kripke function space. And we can see that this is exactly this Kripke function space, but we also have additional condition that this must be a natural transformation. So plus there is also a naturality for this function. So there is some function together with the naturality. Okay, but what about pi? So what if I want to have a pi type in the preshift model? Then it looks like if I have some a which is a type in gamma, and I also have a type in gamma a, then it gives me a type in gamma. And then the defining isomorphism is that the Tm gamma AB should be isomorphic to Tm gamma of pi AB. And this is lambda application. And what can we do now? And here I'm not sure how it can be done, but I try to do something very quickly, which is that I say that the definition should be pretty much the same. So here I have a substitution. So previously I had this substitution, But now, because everything is dependent now, I need to have some TM. So what if I have a TM of yoneda I, but yoneda I has to be extended now with A of something, and then I get B of something. And if I look at A, so A is in gamma, so I need, so this question mark 1 and question mark 2. So question mark 1 should be a substitution from yoneda I to gamma. But I already know that this is isomorphic to, so this set is isomorphic to just gamma I. And I also know that gamma is an element of this. So it is possible to convert an element of gamma I into a substitution. So I can, this is a bit of a hand waving because I'm omitting the yoneda isomorphism conversion, but I can just write gamma here, and then I can also write gamma and Q here. Sorry, and then this is the action of pi IB. I'm not sure if there is, do you know about some exact application of the yoneda lemma, Ambrus, which works for pi types as well?
Yeah, I think it works. Need some yoneda lemma, and it's not worth it. So it's better to just define it directly as you did, in being inspired by the exponentials. I think this was very good.
Okay, I think the time is over, which is very good because what's left of is the Ambush version of two-level type theory in the notes, which I haven't yet reviewed. So we can continue from this the next time.
Yeah, so Raphael can talk about it next time, I guess, no?
Yes.
Yeah, so I think that's good. So after two-level type theory, then maybe we can do a canonicity model and maybe sketch a normalization model. And basically that's all we wanted to say in this series of seminars.
Okay. Okay, I will prettify this note a bit and make it clearer what are the homework parts.
Yeah, thanks.
And upload it.
Yeah, thank you very much. Okay. Okay, then bye-bye.